Hi, this is Mr. Gamboa. We're going over the Pre-Calculus Unit 4, Practice Exam C on exponential functions. Let's get to it. Question 1. So the number of flies on a sad Interstate 5 freeway cow at noon, so say 12 o'clock, right? 12 o'clock, is 12. So at noon, 12 flies on the sad cow. Then an hour goes by, so that means it's 1 o'clock now. And the number of flies grows to 30 total flies, so 30. And then by 2 o'clock, so 2 o'clock, right, the number of flies on the cow is 75. So the first thing we should do here is note, if the pattern persists, what we're seeing here is an example of exponential growth. 12 times something makes it 30, so you would do 30 divided by 12, or 75 divided by 30, because the pattern should be the same, right? I should always be multiplying by the same thing every time. I'll do that division real quick on iPhone. What is 30 divided by 12?
30 divided by 12 is 2.5.
2.5. Okay, so every time an hour passes by, I'm doubling and a halving the amount of flies I had. The actual question says, if the pattern is consistent, then how many flies were on the cow at 10 a.m.? So actually I have to backtrack a bit, right? Not at 11 a.m., but at 10 a.m. So in the same way, we could easily just take the number 12, so the 12 flies at noon, and then divide by 2.5. And I'm going to do that in repetition twice to go from noon to 11 to 10. And then I think the answer ends up being some funky amount of flies. Let me do that real quickly just on my my calculator. 12 divided by 2.5 is 4.8. And then 4.8 divided by 2.5 is 1.92. So it's not a whole number, but it's the thing that makes it work, right? You can check your work by taking 1.92, multiplying it by 2.5 once, and multiplying that by 2.5 again. And when you do that, I do find that the answer is 12. So I know that 1.92 flies is the right answer. Okay, so as you'll see on your real exam, the first question is meant to be done just by kind of constructing a table or a diagram of sorts, right? And you want to think, what is the constant multiplier to go forward? In this example, we have to go back, okay? But it's always constantly multiplying by the same thing. That's the definition of exponential growth or decay. We're constantly multiplying by a number. All right, for the next question, determine if these model exponential growth or decay, or neither actually, because a couple of these are going to be neither. So let's look at question 33, right? So x goes up by 1, right? Because we're increasing by 1, increasing by 1, increasing by 1, right? So every time x goes up by 1, what's happening to the y's? Well, from 50 to 10, it looks like I divided by 5, right? And then from 10 to 2, again, I divided by 5. And unless you're unfamiliar with it, right, 2 divided by 5 is 0.40. So this would be an example of exponential decay in this case, okay? Now, how do I see that? Because you might think, oh, it's growing, I keep dividing by 5. But what I'm really doing is I'm multiplying by 0.5, right? Every time I'm multiplying by 0.5. I don't keep 100% of whatever this is, I only keep half of it. That's equivalent to multiplying by 0.5, okay? So here, since b is a number that's less than 1, right? That's when we say it's decay, right? In particular, b is 0.5. So decay is my answer here. If I go over to this one, 34, again, every time x goes up by 1, what's happening with the y's? Well, you could divide these numbers, 32 divided by 28, to see what I'm multiplying by. But what I would encourage you guys to do is immediately notice that these are all off by 4. What I'm doing here is I'm subtracting by 4, consistently. And again, that you might confuse it just as an English word as decay, but this is an example of neither. Remember, exponential growth or decay is the continuous process of multiplying by something over and over and over again, right? Or dividing, right? But division is the same thing as multiplying by like a decimal or fraction. So we end up saying neither. This is an example of linear decreases, right? Every time x goes up by 1, I subtract by 4. So that's linear, that's not exponential. All right, so we'll try to go through these next ones at a quicker pace. here, as x goes up by 1, it looks like the y's get decreased by 6 every time. So just like that one, because we're not multiplying consistently, we're subtracting here, we would say this is neither. 36, every time x goes up by 1, it looks like 17 becomes 51, becomes even bigger, 153, and then it becomes 479. So this one, I think I can see that in my head. That's times 3. And then 51 times 3, that is 153. And 153 times 3, the 3 times the 3 would make the 9, and I know the 150s will get to 440, so that makes sense, okay? So here it looks like as the x's go up by 1, the y values triple. So this is exponential growth. Okay, because here my b value is 3. That's a number bigger than 1, right? I'm tripling. Obviously it's growing. Okay, we get to the last two, and here you might be prone to freak out because here we see that the x's go up by 5, right? So plus 5, plus 5. And again, don't let that stop you with being able to show how smart you are. In the context of this problem, we could see it maybe this way. Maybe on the 5th day, there was 2 birds in a cage. And then on the 10th day, there was 8 birds in the cage. And then on the 15th day, there was 32. So this is still an example of exponential growth because I'm constantly multiplying by 4, but I'm not doing it every day. I'm doing it every 5 days because it skips over, right? So I mean, a little extra teachable moment here. You have to figure out what did I have at like the start, right? It looks like I would divide by 4 one more time to go backwards. So 2 divided by 4, I think that would have been like a half, right? So at day 0, I started with a half. I constantly multiply by 5, or not by 5. I constantly multiply by 4 because that's what I'm constantly multiplying. And that doesn't happen every x day. It happens every 5th day. So this would be one of these examples, okay? Where when I plug in 5, 5 goes here. 5 divided by 5 is 1. So it's 4 to the 1, or just 4. And half of 4 is 2. So that starts me up right here where I want to be. And then when I plug in 10, 10 divided by 5 is 2, so it's really 4 squared. That's 16, cut that in half, that's 8. So this equation would produce this pattern, right? And like I said, it's kind of onto you to recognize that this is still growth. It just happens not every day, it's every 5 days. So same thing here. This goes up by 2s, right? So if I had to assign this to a word problem, I would say this is more like every 2 days something happens, okay? And here the numbers decrease, and they decrease very quickly. So I wouldn't be suspicious like these ones. I'm not constantly subtracting by the same amount. I'm probably dividing by something. And I can kind of take a sneak peek here. I know 12 divided by 6 gets me 2, right? And if I really think backwards, right? 12 times 6 is 72, so 72 divided by 6, that's what gave me 12. And if you use a calculator, you'll see that 432 divided by 6 is 72. So what I'm doing here is I'm consistently dividing by 6, which is equivalent to consistently multiplying by a 6th, okay? So I'm always multiplying by a 6th. For you calculator people, 1/6 is approximately 0.16 with a bunch of 6's that go on forever. It's like 16%, maybe even 17%. So in this case, I would say this is decay, right? The b value is 0.16, that's less than 1, that's how I know. And it's happening every 2 days. So if you had to think of a word problem that started off with this, maybe we could say, I took some medicine on a certain day, and then every 2 days, the amount of medicine remaining in my bloodstream is decreased by a factor of 6, right? It's decreasing, okay? But this is decay. Okay, y'all. So, very last question, I think. I have to go to the back side of the document. We have the classic money in the bank question. So here it says, say you put away $1,000 into the savings account that gained 6.7 annual interest. So for these problems, and on the test, I will end up putting the formulas, FYI. So these formulas go as follows. You have an initial amount. It's going to gain interest, so the formula will have a 1, because I'm keeping that initial amount, but I'm gaining, so adding that percent 0.067. I move this back twice, right? To convert from a percentage to a decimal. And again, in this situation, I'm not getting that interest all in one go. That annual interest is getting paid out monthly. So this annual interest rate gets divided by 12, right? And so this is representing how much interest I get, in a month. Because there's 12 months in a year, I would put the exponent 12 up there to represent getting 12 monthly payouts of my 6.7%. But in the context of this problem, we want to know what happens if that occurs for 5 years, right? So again, I would multiply here by 5 to let me know that, yeah, I'm getting that 6.7% paid out monthly. That's why I'm dividing it by 12. But I'm getting it a total of 60 times. Why? Because 5 years, 12 months, a year is 60. So what I would actually end up doing for this problem is I would use a calculator. I would take 1,000. I would multiply it times 1 plus 0.067 divided by 12, and then raise that to the 60. Okay, you can do that on the blue calculators. You can even do that on iPhone, for instance. I have a blue calculator here, so I'll show you what you should put in directly. So you start by putting in the 1,000, right? So something like that. You hit the multiplication button. You do a parentheses and put the 1, right? Because we're keeping that 1,000. 1 plus what? In this case, 0.067, so something like that at this step, right? And then that's getting divided by 12, so you do the division symbol, hit 12. You would then close the parentheses. And last but not least, I need to raise that to the exponent, and the button I press for that looks like the button on itself. It looks like a little tent, like, where is it? This here, the caret symbol. And up there, I'm going to put the product of 12 times 5, so 60. Right? So I just put 60. And then I immediately hit enter, and I get my answer. It ends up being about 1396, so 1,396 with 64 cents. I rounded up a little bit there. Okay, so that's how much my initial investment of $1,000 will become in 5 years with that amount of interest rate. Okay. So it ended up gaining some value there. For the continuous situation, right, we don't use this formula anymore. The idea behind continuous is if I get paid out this annual interest by the month, I divide by 12. If it's paid out by the week, I would divide by 52 and then put a 52 up there. And if it was by the day, it would be divided by 365 and a 365 up there. So what happens if I get interest paid out not by the day, but not even by the second, like every moment possible? Then this entire expression just takes on the value of E, like this. So that formula would be like this. We have our initial amount. It gets multiplied by E, the constant of constant growth, raised to the RT. So in this instance, it would be 1,000, because that's my initial amount, times E. A reminder, E is about 2.71 with change, raised to the interest rate. So in this case, it's 0.067. And at this point, what I have here is the amount of money I would have at the end of a year with that annual interest rate. But I need it over the course of 5 years. So as the formula dictates, it's R times T. So up in the exponents, I'm going to multiply 0.067 times 5, because it's happening in 5 years. And what I expect to find in a bit is a number pretty darn close to this. As you saw in our intro activity to Who Wants to Be a Millionaire, when you let interest compound continuously, the amount of money you end up making extra, the interest, doesn't ever really triple. It gets close to 2.71. You can at most multiply by around 2.71. Like, that's how much more you can make from your initial investment, but no more than that. As it turns out, that's just what E is. That's as much interest as you can get. So let me show that. Again, I start by typing in 1,000. I hit the multiplication symbol. To access the E button, I'm going to press the second button, and then I'm going to look for the LN button, which is this one. That summons E for us, and it even creates a little exponent button. And what I'm going to put up there is 0.067 times 5. Okay, so all like that. It already popped up. 0.067 times 5. Close parentheses. I hit enter, and not much to my chagrin, I get 1397, which makes sense. It turns out if I'm able to collect interest every waking possible millisecond, the most money I could get is about like $1 more, and then some. All right, so that's how I would do these problems. Again, on the exam, I'm gonna put the equations on there with a helpful reminder, right? Like you'll see this. Like for this type of thing, use this equation. But if it's S continuously, we know to use E. All right, moving on. Last question in the practice exam says the total number of visitors a certain Instagram account gets T minutes after it's been posted is given by the table. So what we can discern from here is after 42 minutes, these many people have visited that Instagram page. A minute later, there's a lot more. And a minute later, a lot more even there. So it says here, does this table represent exponential growth, decay, or neither? Well, it looks like every passing minute, it goes up. We just got to check if it's by a consistent amount. So I would say, ask yourself the question, 11,000 times what is 12,100? So to answer that question, we simply divide. And if I remember, I think the answer is 1.1. Let me check. 11,000 times 1.1 is indeed 12,100. So then what I would do with a calculator is I would then take that, multiply it by another 1.1, in which I get 13,310, which is what I see there. And then I would just multiply that one more time by 1.1, and I get 14,641. So yeah, it does look like with every passing minute, the amount of views grows exponentially by this factor of 1.1. Like we're getting a 10% increase with every minute. So question for this first one, part A, we would say, yeah, growth. Question B, how many total visitors would have seen the Instagram page after an hour since it's been posted? Round your answer to the nearest whole visitor. So here we have to use a little bit of our literacy skills. When we say hour, we mean 60 minutes, right? So if I know every time 1 minute passes, this initial 11,000 from time 42 gets multiplied by 1.1, the question is, if I write 11,000, and I know it's getting multiplied by 1.1, how many times is that 1.1 getting multiplied until I get to 60 minutes? And if you thought 18, you'd be correct, right? I have to multiply it 18 times because 42 minutes plus 18 minutes gets me to 60 minutes. And that would give me my answer, okay? So then I would just do 11,000 times 1.1, caret symbol to the 18th power, and I get something in the neighborhood of, let me make sure, I'll double check that. I got something that seems slightly big. No, it is what it is, 61159.09. So in terms of the viewers, it's 61,159. We'll round down here to the nearest visitor. So 61,159 visitors. Okay, and that would conclude the practice test, okay? There's an extra credit here. If you want to know how to do that, please approach me. But with that said, I think that's the end of this video. Again, know that the first problem of your real exam will be very similar to this, right? Very similar to the number of books in the Pasadena bookstore, the number of ounces on an Arizona iced tea in a certain liquor shop, right? It always starts with a setup like this, where you find the multiplier and either go forward or go backward a couple of steps, okay? The next question will be determine if it's growth or decay. As we've kind of gone over, it's growth when I'm multiplying consistently by the same number if it's bigger than 1, like 3 and 4 in this instance, and it's decay if I'm constantly multiplying by the same like decimal value, like 0.5 here or 1/6 here, right? If I'm constantly subtracting or adding, that's not exponential growth. That's just linear growth or linear decreases. And our money problems here are just determine the parts of the formula and plug it in. But yeah, I hope this is helpful with helping you study, and I'll see you soon in class. Bye.